Probability is essential for any statistical analysis, and all statistical methods have their roots in probability. So, why is probability important? It's important because probability deals with uncertainty, and uncertainty is in every part of business. Many business decisions are done with a certain element of uncertainty, such as where will the economy be in 6 months? What will my customers spend over the next 2 years? Will my manufacturing output remain constant? It's important to note that there is a difference between risk and uncertainty. Uncertainty provides an assessment of the likelihood of an event. Risk is more related to one's own position to the uncertainty of events. So, for example, let's assume that we have a hurricane and there's a 20% chance of a hurricane hitting the East Coast in July. Well, if you live in Seattle, the uncertainty probability is still the same that it's going to hit the East Coast, but your risk is 0. So it's important to understand the difference between the two. Now, in previous lectures, we've termed our data set as a collection of variables and observations. The variables are the data collection for particular observations. When we have a set of data for a given variable, it's usually collected at random, and it should be. So consider the fact that we have a questionnaire and we ask 100 people or 1,000 people a various set of questions. Well, question 1 would be answered by the individuals and it will have a distribution, and it is therefore a random variable. So let's take an example again of a survey in which you collect 10 questions from 100 people. The first question may be a Likert scale from 1 to 5. Highly likely to highly unlikely. The collection of responses for this variable would therefore create a distribution. We call this a probability distribution because we can assess the probability of receiving a particular response. The chart in the bottom area, you can see that we ended up with 3 responses for question 1, about 7 responses for question 2, 14 responses for question 3, and we can see the distribution of the answers for each one of the answers for that particular question. Now, probability is the likelihood that an event occurs. It's always a number between 0 and 1, because if an event can never occur, its likelihood would be 0, and if an event can always occur, its likelihood would be 1. Everything in between 0 and 1 is the probability of the event occurring, and is therefore a measure of the uncertainty of the event. So let's take an example. If we had a 0.33 probability, that's a 1/3 chance of the event occurring. That would be synonymous of saying having 3 cards and choosing 1 at random. The likelihood of choosing A is the same as choosing B is the same as choosing C, each one having a 1/3 chance probability. If we have a coin flip, the probability is 1/2 or 50%, 0.50, that we would have tails or have heads. Now, given the complement rule, this is the opposite of an event occurring. So if the probability of A occurring is 1/3, then the complement, or the probability of A not occurring, would be 1 minus 1/3, or 2/3. So mathematically, we will denote things as the probability of A equal to 1/3. The probability of A complement equals 1 minus the probability of A. And that's how we obtain 1 minus 1/3, which equals 2/3. Thus, the probability of choosing not A, which means choosing B or C, is ultimately 2/3. The addition rule provides the probability of mutually exclusive events occurring. So, for example, let's assume we have a regular fair die with 6 sides. The probability of any number coming up is 1/6 on a single dice. If we wanted to know the probability of 1 or 2 coming up on a single dice, we would simply add the probability of each occurring. We can denote this as the probability of 1 being 1/6, probability of 2 being 1/6. So the probability of 1 or 2 occurring is adding the 2 probabilities together and giving 2/6 or 1/3. Now, once again, let's assume that we have independent events. In this case, we have 2 rolls of the dice. However, we want to know the probability of a combination of events, such as the probability of rolling a 1 and the probability of rolling a 2. In this case, we simply multiply the probabilities of each event. So for the probability of rolling a 1, we have 1/6, and the probability of rolling 2, we have 1/6, again, on one dice and on the other dice. So we mathematically denote this as the probability of rolling 1 and the probability of rolling a 2 on the second dice, 1/6 and 1/6. This would be multiplying the 2 probabilities together to get 1/6 and 1/6, which is 1/36. Consider the fact that you have a full set of possibilities where you have 1, 1, 1, 2, 1, 3, 1, 4. If you wrote all those out, you would end up with 36 possible events. And specifically what we're asking for is the probability of rolling a 1 on the first dice and a 2 on the second dice, and that can only occur in one of those sequences of the 36 events, and that's how we end up with 1 over 36. Now, conditional probability gives us a way to assess the probability of an event given the fact that another event has already occurred. We need to know the probabilities of each event, which we will write as the probability of A and the probability of B. And we're given this formula here, and we read this as the probability of A given B is equal to the probability of A and B divided by the probability of B. Now, on this next slide, we actually show just a little bit of algebra to show some similarity here, but that we have the probability of A and B, again, in a conditional probability sense where there's a dependency, is equal to the probability of B times the probability of A given B. And we see that on the right side from the equation that we've had before. So as an example, let's say we want to know if a project will be on time. We know that meeting our specified deadline is due to receiving our inventory on time. We estimate that our chances of getting the inventory on time is 2/5 or 40%. We also estimate that if we receive it on time, our chances of being on time with the project is 3/4 or 0.75. So mathematically, we will have the probability of delivery being on time as 2/5 and the probability of being on time given the deliveries on time as 3/4. So the probability of being on time and delivery on time is basically the probability of B times the probability of A given B by the formula above, which is equal to 2/5 times 3/4, which is equal to 6 over 20, giving us 0.30, or a 30% chance of being on time and delivery on time. Now, you may ask, well, where do I get these probabilities from? Well, these probabilities may come from a number of different sources, but suffice it to say that someone has assigned these probabilities either empirically or through experience. They've said that we know that there's a 40% chance of having the delivery on time, and that if we have the delivery on time, there's a 75% chance of us meeting our deadline. So ultimately, we decide that there's a 30% chance of us meeting our being on time and the delivery on time together. We can further look at this using a probability tree. So we have what's called the tree of probabilities, where we list all the possible combinations. So on the left part of the tree, we have the probability of the delivery being on time, which is 2/5 or 40%, and the probability of not getting the delivery on time on the bottom half of the tree, which is 60% or 3/5. Now, given the fact that we have the probability of being on time with the project and the deliveries on time, it will be 3/4. And we'll multiply that together for that third bullet point, or the third circle out there. So we assume before the probability of being on time, given the fact that we have delivery, is 3/4. The bottom half of that top tree will basically be 1 minus 3/4 or 1/4, because it's the probability of not being on time given the fact that the delivery is on time. Now, on the bottom half of the tree down below, we separate again into two segments where we have the probability of being on time given the fact that the delivery is not on time, and we have the probability of being not on time given the fact that the delivery is not on time. And we have our 1/5 and 4/5. Again, we would have been given those probabilities from some sort of estimation. When we multiply this out, we find that the probability of being on time with the project and the deliveries on time is going to be 30%, doing the multiplication across. We also find that the probability of not being on time with the delivery on time is about 10%. Then we also find that the probability of being on time and the delivery not on time is 12%, or 0.12, and the probability of not being on time and not having the delivery on time is about 48%. Or 12 out of 25. Now, obtaining the probability measures can come from two primary sources: individual or institutional subjective assessments of situations, or through empirical observations. So A subjective probability is one in which the probabilities are done where individuals have made a guess or an educated guess, and these may come through institutional assessments. Something within the company or organization knows by experience that it's approximately 30% or 20%, and these probabilities are usually made in an easy-to-interpret probability, such as 0.30, a 30% chance, a point three-quarters chance, or 75% chance. You'll rarely see subjective probabilities being 36.5%. So they come from experience and collective knowledge. Objective probabilities, however, are the probabilities where empirical data is collected and the probabilities are assessed from the data estimated from larger data sets. So what will happen is we'll collect some data and we'll actually calculate what these probabilities are in order to do assessments. A relative frequency refers to the number of times an event occurs over the span of all events. We might calculate the relative frequencies of a customer's purchases in a month and possibly aggregate those purchases by a group of customers to determine the relative frequency of purchases for the group. So we may collect all the data for high-value customers and low-value customers and begin assessing these determine the frequencies of high-value and low-value customers, aggregate them over time, and determine what the general probability would be over time. As we get more and more sample data, our relative frequency from our samples will tend to the true probability of the larger population. We know that as we add more and more data, we will tend to what the real number should be. This effect is known as the law of large numbers.